Okay, welcome to Monday, November 9. A couple more people in the room here. And our subject this whole week is trigonometric equations. And that's a pretty nice and focused topic. So that is not so bad. We need to be, really careful that we follow the directions exactly on this because of the variations of the problems you're going to see. But these all have a very clear and definite goal. So it's not hard to get used to the variety of the equations that you're seeing right here. And basically the idea is these are equations that have trigonometric functions in them, or someone is supplying you with the values of a trigonometric function and asking you for the angle that produced that. And it starts from simple and works way up through the more complicated ones using, algebra techniques that you've used previously. So I'll just take you to our website here just to make sure we get oriented today. We're looking at sections 6.1, 6.2, and 6.3 this week. And we're just going to pick out problems from these three sections, work on examples of problems in these three sections. So we'll probably get into, probably far into section 6.2 today. You have, if you're looking ahead, a homework problem due tomorrow, and then a following homework problem is posted. And then for whatever form it takes, you have, get somebody else in the room here, you have Thanksgiving coming up, and I don't know what form Thanksgiving is going to take, but there will be a homework due on Tuesday, November 24. You can look at the global homework list here in the back. On Tuesday, November 24, but there are no class sessions at Delta College in any classes on Wednesday, November 25. So traditionally, Wednesday, Thursday, and Friday are the Thanksgiving break. So you've been in the habit of handing things in on Tuesdays, so that's not going to affect that. But I just want to give you a heads up that Wednesday, November 25, we do not have a class session. But that's 16 days from now, so we have time to remind you again. Okay, I'm going to go back to week 11, and let's just pick out some problems in that section. And I think for a while, I'm going to take one from each section. I also announced that, exam 1 and grade reports are posted, and you could look over those and compare them against the solutions. I don't mind if you want to ask any questions about any particular problem or such, but do look at the exam, do look at the solution that was posted so you have a feeling for how a problem could have been done. And I was very particular about the directions, so make sure that you're looking carefully at the directions, exactly what was requested when you were doing the problem. But I don't mind at all if you want to ask a question about graded this way or graded that way. If I made an error adding points or taking away something I shouldn't, I'll certainly refund it to you. But I was very strict in people following the directions. Okay. So let's look at an ordinary example like 6.1, number 3. And these are the important instructions you have to do here. When someone asks you to solve a trigonometric equation, since you know the trigonometric values repeat, you could probably find lots and lots and lots of solutions repeating over and over again. Don't wear yourself out if that's not what they're asking for. So make sure you only report the answers in the intervals that they request. Make sure that you use radians or degrees as they request. This book seems to have a habit of when he writes a theta, he asks you to give the answer in degrees, and when he writes an x or a t, he has to give you the answer in radians, but just check the directions. Use the exact values. Do not use a calculator, and particularly when the problem says do not use a calculator. Do not approximate unless they ask you to approximate. And then, if they do specifically ask you for all possible solutions, then there's a way to present that too. But I don't want you to go to that trouble unless it's asked for. So we might come across some like that later. And we will come to some that will approximate in a second. So solve, in this case, for theta in this interval from 0 to 360. And the equation is 2 cosine theta minus root 3 over 2 equals 0. So we're going to start you off on a basic one right here. And the solution to almost all of these is going to involve a picture. So if you want to find out what theta is, then first you have to find out what the cosine of theta is. You add root 3 to both sides. You divide both sides by 2. That will tell you what the cosine of theta is. Just added root 3, divided both sides by 2. And then they expect you now to look at that and say, I know what angle this person is talking about. So you draw this angle. But there is more than one angle that has that cosine. Cosine root 3 over 2. Now, if you want to scratch on the side, x over r. But what triangle is it that has a radius of r and an x of root 3? This is going to be a 30, 60, 90 triangle. I can fill in the third side with the Pythagorean theorem, or I can fill in the third side because I've memorized this ratio. This third side is going to be length 1. And so this point right here is root 3 comma 1. And I know this angle is 30 degrees. But now I have to give all the answers that are valid between 0 and 360. I can't go around and come back and land on that. That would be 390. But there is another angle, the mirror image, that will have cosine with minus root 3 over 2. That's not going to work. But there's another angle, mirror image, they would have cosine of root 3 over 2. Let's take that same x value. Let's take the y value to be minus 1. And let's take the radius to be 2. So these two angles have the same cosine. Remember, cosine is adjacent over hypotenuse. And since these two angles have the same adjacent and the same hypotenuse, then they have the same adjacent over hypotenuse. This is 30 degrees. This is also 30 degrees, but 30 degrees shy of 360. So this is 330 degrees. So then that's how you present the answers. Theta equals 30 degrees or 330 degrees. This one won't work because this would have a cosine of negative root 3 over 2. There's another mirror image over here. And that would also have another cosine of negative root 3 over 2. So sines and cosines come in pairs like that. Okay, so solve for trig function, draw a trig function, write down all the angles that were requested. That is the general procedure. Let's try something like 11. So I just want to work our way through some progressively harder ones. Here they want you to use radians. Okay, so let's say solve for x between 0 and 2 pi radians. Give all the answers exactly, do not use a calculator. So let's say I'm looking at 11, says 3 sine x minus 5 equals minus 2 sine x. Solve for the trig function, then solve for the angle. So I have to bring these sine x's together. If I add 2 sine x to both sides, I have 5 sine x. If I add 5 to both sides, I have 5 over here. And this can only be true. Divide both sides by 5. If sine x equals 1. That's a special angle that I have to recognize immediately. It's only one special angle. Remember, sine is y over r. So if the ratio of y over r is 1, then y and r are equal. And where is it? It's a sloppy unit circle. But where is it on the, go ahead. Oh, sorry. Go ahead. You're asking me to erase the paper, my fault. Where is it that the y value and the r value are the same on this quadrantal angle right here? We're commonly calling this 90 degrees, but in terms of radians, it'd be pi over 2. And this does not come in pairs because if I go the opposite direction, I have a sign of minus 1, not 1. So this only has one solution. And that is x equals pi over 2. And I can't say something like, oh, draw the triangle here. I mean, this is a tall, extremely thin triangle, or a tall, zero width triangle. It's not a triangle like I drew a triangle in the previous problem. Now, I'll give you a preview of what happens if they asked for more answers. In the problem above, these are the only two angles between 0 and 360 that work. But you know that if I keep adding 360 to either one of those, I would get an answer. So I could say 30 degrees plus 360 times k, or 330 degrees plus 360 times k. And when someone says something like that, although I won't write it down right now because he hasn't asked for it yet, then you're just saying, and go around the circle once, and go around the circle twice, and go around the circle 3 times. So you can go around the circle as many times as you want. Pi over 2 has a sign of 1, but so does 2 pi plus pi over 2, which is 5 pi over 2. 5 pi over 2 is not in this interval. All they wanted you to do was collect all the answers in one circle. Okay, good. Next step. Now let's do something where I need a calculator, I need to approximate. So you use the exact values unless they ask you for an approximation. But when they do ask you for an approximation, then you have to be able to perform. So let's look at problem like 15 or 17. We're still doing mellow ones, but it just sets the standard here. So I'm going to try 15. Say, solve, find all solutions, theta, 0 degrees, less than theta, less than or equal to 360 degrees. And then he even says, if that includes 0 and 360, go ahead and add them. But on the last step, you're going to need a calculator because you don't have an exact answer, and they want you to answer to the nearest tenth of a degree. So here's the problem. 2 cosine theta minus 5 equals 3 cosine theta minus 2. Procedure is still the same. Oh, let me get someone else in the room here. Excuse me. Procedure is still the same. Solve for the trig function, then solve for the angle. So I can subtract 3 cosine theta from both sides. I can add 5 to both sides. That's making me very nervous. If I add 5 to both sides, what do I get? A physical 3? Now that should really make me nervous. But we have to go forward with the problem. The thing I do at this kind of stage is, did I copy that right? Because already I recognize that this is impossible. On the other hand, if it's impossible, it's easy to write down all the answers. You say there are no answers. So first of all, if I divide both sides by -1, the cosine of theta is -3. Well, the cosine of any angle is never more than 1 or less than -1. So this is where I double check what I wrote. And I have to accept that we wrote this correctly. We simplified it correctly. And so therefore, there is no solution to this problem. I was all excited that I was going to be able to approximate something on a calculator. Guess I have to go for the next problem. Cosine of theta is never -3. I mean, cosine is x over r, and x over r, ratio of 3 to 1 negative, isn't possible in any triangle. X and the y are always never bigger than r. Okay, let's pop into 17. I guess it's good that he throws 1 in there because he ought to be keeping us honest. So let's say find all solutions. For theta between 0 and 360. And this time it is sine theta -3 is 5 sine theta. And we're going to try fancier ones in a second, but I do like the way he sets this up, just slowly increasing the difficulty of the problems. Okay, subtract 5 sine theta. 1 sine theta minus 5 sine theta is -4 sine theta. Add 3 to both sides. Divide by -4. So you have to do all the ordinary algebra stuff correctly. Now I can draw this angle, but it's not a famous angle that I know, right? I'm looking for, sine y over r equal 3 to 4. I can certainly draw that. And I want the y to be negative. The radius is never negative. So I'm thinking it's going to look something like this. I haven't filled in the details yet. And remember, this side is going downwards. So this y value is -3. And the radius is 4. This would give me a sine of -3/4. Let's fill in this other side here. 3 squared plus x squared equals 4 squared. X squared, 9 and 16. 16 minus 9 is 7. X is plus or minus √7. So this could be √7 right here. And in this quadrant, I would say minus √7. But also admit that you could have had the mirror image over here. 3, 4, and √7. But then the name of this point would be plus √7 and -3. So the √7 was irrelevant. Both of these angles have the sign of -3/4. And just to see what both of the angles mean, I mean the angle that starts on the x-axis and swings past 180, and then this angle that starts on the x-axis and swings nearly all the way around. But that theta is not a famous angle. I need the calculator to tell me what that is. And they want degrees, and they want the nearest tenth of a degree. So I need to ask the calculator, what angle has a sine of -3/4? And make sure I'm in degrees. Pull out my calculator here. Clear, clear, got it. Let's check that we're in degrees. Okay, we're in degrees. Next problem, I have radians. Can I get something that will obviously raise this calculator screen? Books are so in the way. Let's try this. So I'll say sine inverse. Get out of here. Sine inverse -3/4. And remember that this answer is going to come to me in a particular way. It's not going to be the way I want to present it in the problem, because the calculator responds with -48.59. And let's say to the nearest tenth of a degree, -48.6. That is correct. But it is not between 0 and 360. Which one of these angles did they just give me? I haven't tried to draw this perfectly, but I'm guessing that this must be an angle of -48.6 degrees. Now it's my job to convert it to these two red angles. To convert to this angle with the same terminal side, I'll just add 360. So to go almost all the way around, it'll be 311.4. Excuse me. To give this angle over here, I'm going to do 180 plus this size of an angle, which is 48.6. So I can take the 48.6 as a positive angle and add 180 to it. I could also say it like this. I could take 180 minus the negative 48.6, but I'm going to write it like that. 180 plus the opposite of that number. I had to decide whether my calculator likes me to write like that. We'll find out in a second. 228.6. So it forgave me for writing a double negative. Okay, so I clearly have the two answers by the image. That's why you almost always have to draw a picture for all these problems. I clearly have the two answers, but it was not the way the calculator presented it to me. Because remember, when the calculator does an approximation sine inverse, the calculator only works between minus 90 degrees and plus 90 degrees. You had to put these in the proper format. And then to even know that there were two answers, you had to draw a picture of the situation. So these are the things that are behind the scenes in these problems. Okay, let's try another one. And we're working our way through there, and we're not doing too bad. And he's got some funny word problems in the end of this section that we'll look at too. I'll keep the Rubik's cubes around to elevate the calculator. So he's going to remind you of using the quadratic formula and solving equations before. Let's look at 23. And while we're working here, let's label the papers. Okay, thank you. So we want to solve on the interval 0 to 2 pi. And now, again, I'm going to say be very careful about their directions. Notice on this problem, he says 2 pi is not an answer they're asking you for. If you came up with x equals 2 pi, that's not the answer they want to hear. So be very careful whether they're including the endpoints or not here. And traditionally, they include both endpoints, but he just wants to prepare you for the people that do it this way, which is also acceptable. 23. Sine x plus 2 sine x cos x equals 0. And then I might show you a nice picture of this so that you're comfortable that we're actually getting the right answers. Well, this is a problem where I've got multiple trig functions to look at, right? So really what I have to do here is remember old algebra techniques that when I'm trying to solve an equation set equal to 0, or if I set an equation equal to 0 to solve it, I factor out common terms. Both of these terms have sine x in them. You factor out the sine x and you're left with 1 plus 2 cosine x. And that in itself gives you two possibilities. In algebra, you call this the zero product principle. That if you multiply two things to get 0, one of them is 0. Sorry, sine is 0, or 1 plus cosine is 0. I'm missing a 2 somewhere, right? So let's make sure you always factor correctly. If I pull out a sine x, there's left with a 1. If I pull out a sine x, there is a 2 right there. So watch yourself every moment. Okay, I know how to draw sine x equals 0. Sine x is 0. Remember, y over r. These are quadrantal angles. They're very flat triangles. Through the point 0, 1 with radius 1, or through the point 0, minus 1. Sorry, I got the numbers reversed. 1, 0 with radius 1, or -1, 0 with radius 1. And this is 0 degrees or 180 degrees. Notice 0 degrees is one of the answers they want. Oh, okay, now you're thinking radians too, right? So you might naturally think in degrees, but he said give the answer in radians because he said 0 to 2 pi, exact values. So I got to say 0 radians or pi radians. So 0 is an acceptable answer. So here's 2 possible answers we have so far. Now we draw this graph. And this says subtract 1. 2 cosine x equals -1. Cosine x equals -1/2. So you have to be very proficient at drawing triangles. Cosine is negative where? In the second or third quadrants. And having this equal to 1 and radius equal to 2 is famous triangle. This side will be √3. And this point will be -1 plus √3 with radius 2. And this side will be -1 and minus √3 and radius 2. 30, 60, 90 triangles. So this is 60 degrees short of 180. And see there, I go thinking in degrees again. 120 degrees. That's 1 pi over 3, 2 pi over 3, 3 pi over 3. Let's state it in terms of radians. And this is 3 pi over 3, 4 pi over 3, 240 degrees, or 4 pi over 3. But these are the only values for cosine is -1/2 in the first circle. These are the only values for sine is 0 in the first circle. So what's the answer to this problem? All 4 of these values. But to make it more real to you, I want to show you a picture. 0, pi, 2 pi over 3, and 4 pi over 3. In other words, if I graph this function, if I graph sine x plus 2 sine x cos x, I'm expecting in 0 to 2 pi to see 4 places where it's 0, and I'm expecting to be able to see those places. Since these are exact values, I'm hoping that I get to see the exact values. Let's pop over to Desmos. Let me get it up. And then I'll bring in. Got it. I'll expand that screen slightly. So let's graph y equals sine x plus 2 times sine x cosine x. Now, it doesn't like me to write like this for some reason. You see the use parentheses around the argument of sine x. In other words, it says he doesn't know where my arguments start and stop. Is the cosine x times this x, or is it times the sine x? So you could do this very carefully like that. Or if you prefer to write the parentheses always around the argument, this is always sufficient. So either one of these will produce this curve right here. Now, what about the 4 answers? I guess I'm going to get rid of the blue one for right now. They are the same graph. So let's not have more writing than we need. But 0 to 2 pi, no, it's not thinking in terms of pi, right? So I'll tell this to think in terms of pi. My answers were involving pi over 3, right? Let's see if I can tell it to think in terms of pi over 3. Well, it thinks in terms of pi right now. Let me tell Desmos to only graph 0 to 2 pi. That might take away some of the distracting repeating. That's kind of nice. Notice I could type in the less than or equal to and the less than. And now I can expand this. Well, that's not the way I want to expand it. Let's zoom in here, and my pi over 3 kicks in. So where are the answers? 0 and pi. 2 pi over 3, 0. And 4 pi over 3, 0. Notice at 2 pi, I get another answer. It's funny that it doesn't, see, it doesn't want to write 2 pi there because I excluded 2 pi in my instructions. So I don't want to report this answer over here at 2 pi because they didn't ask me to give an answer if it was equal to 2 pi. But this is not a bad way to see the 4 answers. 0, 2 pi over 3, pi, 4 pi over 3. Notice I didn't list them in order, and it's not particularly required. I listed them in the order where they came from. Okay, very good. Let's try it with another approximation problem, and let's get out our friend, the quadratic formula. So let's look in problems like 33 to 38. Write expressions using all these solutions to the, okay, so, and then he wants you to write all expressions. So we'll look at something like that in a second. Good. So we already mentioned that, setting you up for that. Okay, so let's take something, quadratic formula. Let's look at 37. So you have to be prepared to use all your previous algebra knowledge. Quadratic formula, all solutions between 0 and 360 to the nearest tenth of a degree if necessary. This time he's bringing us back to degrees. So that's the way we often naturally think. But the problem is 4 sine squared plus 1 is 4 sine theta. This might make an interesting graph too. Oh, let me go back to my paper. We'll come back and make a graph of this later. Okay. I have to visualize a quadratic equation here. And I have to remember what the quadratic formula says. So I remember that I had a formula for solving anything that looked like this. And I remember the formula. You can write this on your formula sheet if you want. I think this is one formula I don't have on your formula sheet. Just thinking I was doing trigonometric formulas. How do I see that here? I see that I have an equation here, but instead of x squared and x, I think I have sine squared and sine. So I'm thinking in my mind, x is like the sine theta. I don't necessarily want to formally write that like that. Let me first of all just organize it that way. 4 sine theta squared minus 4 sine theta plus 1 equals 0. So this looks like a quadratic equation. I just have sine theta in place of x. That means I can use this formula. And I can put sine theta where I see the x. Writing down here that the a is 4 and the b is minus 4 and the c is 1. That doesn't cost me anything to insert those 3 numbers over here. And I just treat this sine theta as the thing I'm solving for. How did we say it at the beginning of the class? First solve for the trig function, then solve for the angle. So now let's use the quadratic formula. Opposite of b, and I have to let you perform this, and you have to perform it accurately. You have to respect all the signs. I generally do that by multiplying really carefully with parentheses and filling in all the parentheses before I start working. 4ac, 4 times 4 times 1. Now, as it happens in this problem, it looks like I'm going to get some breaks. But let's keep working so everybody sees that. The opposite of minus 4 is 4. But under the square root, this was not necessarily what I wanted. This is too generous. I'll have to try another one like this. Do you see that I get 16 when I square minus 4? And then I subtract 4 times 1, which is also 16. Bottom is 8. So I'm going to get an answer, yeah. But I don't have to do any fancy work with the square roots because square root of 16 minus 16 is 0. So this whole thing becomes 4/8, which is 1/2. Now that is not a fancy estimate with calculator problem. We can pull out a calculator, but I can draw the angles that have sine 1/2. I know them because they're famous. Sine 1/2, y over r. That means up 1, radius 2, up 1, radius 2. Names of these points I can name by the third side, 30, 60, 90 triangle, minus root 3 on the left, plus root 3 on the right. I also remind you of this, that, and the book follows the same convention. I label these triangles with the same side lengths because they have the same side lengths. But the x coordinate on the left is negative and the x coordinate on the right is positive. That's where I put in the different signs. This is 30 degrees. This is 30 degrees less than 180. So that makes it 150 degrees. So I was looking for some more excitement on this problem, sorry. I didn't need to use a calculator to do any approximation. Quadratic formula came out too sweet. So the answers are 30 degrees or 150 degrees. Okay, I don't think that's a really good illustration because you have to be able to learn to work the calculator at this step right here. So let's try another one. Let's try 35. And then we'll jump into section 6.2. Also notice, I'm going to add this one at the bottom of the page because I just have a little bit of space. Problem 43, it says, write all of the solutions to problem 11. And we said that earlier, but I just want to write it down. Problem 11, if I bring it back here, only had one answer between 0 and 2 pi. And that was x equals pi over 2. But if I'm allowed to use any number of trips around the circle, positive or negative, then I could present all solutions by saying add 2 pi, add 4 pi, add 6 pi, subtract 2 pi, subtract 4 pi, subtract 6 pi. Well, there's a common way to do that, and that is don't write down all the possibilities. Just say pi over 2 plus k times 2 pi. And when k is 1, you've gone once around more. K is 2, you've gone twice around more. K is minus 1, you've gone backwards around 1, and you'll be at negative 3 pi over 2. This covers you legally and expresses all solutions. That's what he's looking for in that problem. Oh, sorry. Erase the paper. Writing plus k times 2 pi covers you if someone is asking for all solutions. In this case, I only had pi over 2 as a solution, so I don't have to write any others. If there were other ones, I might have to add a 2k pi to those two. I'd have to depend on see what the case was, but this covers me for all solutions to problem number 11 over any interval. Okay. Let's do something where I need to use the quadratic formula, because that last one was not satisfying. Let's look at 6.135. Cosine squared theta plus cosine theta minus 1 equals 0. And how do you remember the quadratic equation? Well, you write it down until you've memorized it. So it never hurts to write it on the side. You're going to use it anyway. So I'll just remind myself right here. What am I thinking of here? I'm thinking of the cosine theta as the variable x right here. I'm thinking of the a, b, and c as the numbers I see right here. 1, 1, and minus 1. C is minus 1 there. So I'll write that exactly. Cosine theta squared times 1. 1 times the cosine theta, just making it really clear what numbers are there. Minus 1. Okay, now let's solve for the cosine of theta. I just insert the a, b, and c. Never hurts to write down the a, b, and c. A is 1, b is 1, c is minus 1. Make sure you don't disrespect one of the minus signs. So I write down opposite of b plus or minus the square root of b squared minus 4ac divided by 2 times a. Now, if I was doing quadratic formula in an algebra class, which I'm doing in another algebra class, but that's on Tuesdays and Thursdays, I would teach people to use the quadratic equation by writing out the formula with parentheses and then inserting the numbers. Opposite of b squared, 4 times a times c divided by 2 times a. Even if the numbers are really simple in this case, you got to concentrate on squaring the proper number, multiplying the proper numbers here, respecting the signs, -1 plus or minus the square root of 1 plus 4. -4 times 1 times -1 is plus 4 over 2. Now I'm going to need a calculator. Now this is kind of interesting. Remember, they want 1/10 of a degree, nearest 1/10 of a degree. So what I have here recalls two answers. So cosine of theta is -1 plus root 5 over 2, or cosine of theta -1 minus root 5 over 2. Now, these are not numbers that I know off the top of my head, so I'm physically going to type this into a calculator and ask the calculator who has that cosine. I could draw it. I can certainly draw it, but it's not going to be a famous triangle I recognize. So first, let's just ask the calculator what it thinks. But remember, the calculator only responds with one number, so I have to interpret what the calculator response says. So first, let's get the calculator's response, and then we have to answer between 0 and 3/60, the nearest 1/10 of a degree. So there's a human in the loop here. You have to interpret what the calculator says in both those cases. Get my calculator stand back. Get my calculator back. Clear. I am in degrees. I had already checked that. So cosine inverse of parentheses -1 plus the square root of 5. Make sure you're using the proper number of parentheses. That's the numerator. And divided by 2. So it's, after you did all the good work, it's kind of worthless if you type this in wrong. So make sure you type that in exactly as it's written, and the calculator here makes me type it on a straight line. So 51.8 degrees. And here, I get a little benefit that I just have to change that plus sign to a minus sign. So I've shown you this key before. At the very bottom, it says entry. Just say second function entry, and you can change that sign to a minus sign. And calculator says, whoops, I typed in something bad. That's interesting. Now, we haven't done anything wrong necessarily, but we're going to have to investigate, right? And earlier, I did this problem where cosine is not -3. I wonder what that number is. Maybe that number is too big. And I think that's the case, -1, -2.2. Let's find out what that number is. I'm not allowed to take the cosine and get a number that's below -1 or above +1. So they give me this fancy error message, but let's just quit and ask the calculator, what's -1 minus root 5? Divided by 2. -1.618. That's good. there is no angle that has a cosine of negative 1.6. So I get no answer out of that branch. Now remember, I'm not done because the calculator only gave me one answer. So this is what the calculator says. I have to draw this and see what all the answers are between 0 and 2 pi. So let's imagine an x over r of minus 1 plus root 5. Now just for numbers, what's minus 1 plus root 5? Just to attach a number to it. 1.236. Approximately. So that over 2 would be something like 51 degrees. Radius 2. And this side minus 1 plus root 2. Plus root 5, excuse me. This side, I don't know what this is, and I'm not particularly interested, although I could use a Pythagorean theorem. 51.8 degrees. Now, where else is going to have this ratio? Same x value down here. I could go negative 51.8 degrees. But that's not in my interval. I have to make it in that interval. So I could say 51.8 degrees shy of 360. So it's 360 minus 51.8 be 308.2. Right? Take 360 minus that number we got up there. 308.2 to the nearest tenth of a degree. So negative 51.8 is not in our answer range, but 308.2 is. I got no answers over here. So approximately, and tell people you're approximating if you are.
Can't see.
Now, excuse me. Approximately, you have 51.8 or 308.2. Okay, that was a more realistic problem because I had to use the quadratic formula. But don't forget, now sometimes you get answers over here too. I think maybe we got lucky that this number became unusable. But don't think that that's always going to happen. So these two numbers came from over here. So you have to execute the quadratic formula correctly, then you have to interpret it correctly, and pick the answers in the space he wanted. Okay, good. That's a very good sample of problems in 6.1. And now I'm going to look at problems in 6.2, and they're almost exactly the same, except he brings in the other trig functions. So we're going to do exactly the same thing we did. We're going to bring in the other trig functions. Oh, by the way, I'm kind of curious. Say 51.8, 308.2. I said I might graph this. Let's try and graph it just for kicks, because I'd like to see those two answers. Although degrees is not Desmos' specialty, but let's deal with it. Can we tell Desmos to use degrees? I think we can somewhere. Well, first of all, let's write the function. Cosine of x squared plus cosine of x. So I'm protecting the argument with parentheses, minus 1. Got it. So here are my two answers. I would swear I was going to be able to use degrees here somewhere. So and where was I going to get to do that? Oh, yeah, it's too obvious, staring me in the face. Bottom. Okay. Now, then it gets super unsatisfying, right? But that's because degrees, 360 degrees, very large. I need 51 and 308. So let's run this by every 30 degrees. And let's run this from 0 to 360. Okay, there we go. Now, it's not a remarkable looking graph, but I can check where it crosses. 51.827. 308.173. So to the nearest tenth, 308.2 and 51.8. So I always have a way to check. I always have a way to check. Just I had to pop into degrees here and give the right interval so I could see the big picture. Okay, good. So when you're doing these, keep that in mind, that you don't have to wonder if you got the answer right. You can always try to graph it and see if it matches what you came up with. Renumbering. Okay. Excuse me. Let's do a couple in 6-2. And our goal this week is 6-1, 6-2, and 6-3. So in 6-2, he does the same work, but he says, let's use the other trig functions alongside these. Let's look at a mellow one to warm up. 6-2, number 5. And think about it this way too. Your job in these problems is to make sure you've covered every possibility. So write the equations. If they're in theta, give the degree answer 0 to 360. If it's in x, then give the answer in radians between 0 and 2 pi and give exact answers. So in this problem, since I'm using x, you want exact answers in radians. Zero to 2 pi. When you do a problem, check off exactly how they want the answer presented. 4 sine x minus 2 cosecant x. Okay, now this is not a trig identity problem, but it is a problem where I have to remember my trig identities. So what I have here is a sine x, but I also have a fraction, but the fraction's made out of sine x too. Cosecant is 1 over sine x. So this says 2 over sine x. And this says 4 times sine x. So how am I going to resolve this, solve this equation, right? I have to combine these into one fraction that's set equal to 0. Zero product principle says when you multiply two people and get 0, one of them 0. But when you divide two people and get 0, only the top can be 0. So let's create common denominator of sine x, So this says 4 sine squared x over sine x. I'm just writing out every step. You can do this faster if you want to. And then you can say 4 sine squared x minus 2 over sine x is 0. And now you have to remember that a fraction is 0 only if the numerator is 0. In fact, you got to forbid the denominator from being 0. So we'll watch that. I do know when sine of x is going to be 0, right? But I cannot allow that. Okay, so I say this because first thing you say is, oh, you just erased the denominator. No, I didn't erase it. I just am studying the numerator. And I have to make sure I never allow that. Okay, so now let's go about solving here. Here's a square root. Well, here's a square, so I'm going to get some square root action. Add 2, divide by 4. Sine squared x is 1/2. If I add 2 plus 2, divide by 4, 2 divided by 4 is 1/2. This gives me sine of x is plus or minus the square root of 1/2. When I take the square root of both sides, I have to introduce the plus or minus. And I do recognize this angle. Square root of 1 is 1, square root of 2. What angle is this? They want it exact. So x over r, y over r, sine is y over r. And 1 to root 2, that's the ratio of 45, 45, 90. But now look at what's going to happen. You have 4 chances to do this. So 45 degrees. Here's a 1 over root 2. Here's a 1 over root 2. Here's a minus 1 over root 2. Sorry, I erased the paper. And there's a minus 1 over root 2. So I've got 4 chances to make this true. I know that these two sides are 1 and 1 also on a 45, 45, 90 triangle. So they're totally labeled these. And I know the angles are 45 degrees. Oh, I guess 135 degrees. He wants radians, right? Because I said, so never forget that. And that's why it's good to write it down at the beginning so I don't screw it up. Okay, I'll convert to radians. So we do sometimes naturally think in degrees. Pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. Now you've reached the place where he's going to take it for granted that you know those angles by name, always and immediately. Okay. Now I could take this and graph it and see what it looks like. Now I cannot allow sine x to be 0. I got to remember that. But sine x is not 0 in these 4 places. So I'm good. I don't have to throw anybody out. And this graph might not be as pretty as the others, but I'm going to show it to you anyway because I want to emphasize you can always see these numbers graphed. So where's the equation? 4 sine x minus 2 cosecant x. I can actually type that in decimals. Let's get rid of that. Let's get to radians. Let's stop the 360. So let's just go to 2 pi.
You're not sharing your screen.
Good, thank you. Pop it over, thank you very much. Okay, so I turned off the degrees, turned on the radians, 0 to 2 pi. Let's make this, pi over 2 or something. Desmos kicks in with a scale when it wants to. And let's retype this. 4 sine x. I'm going to use the parentheses to protect the x. And you can type in minus 2 cosecant x. Gives you a funky graph. And down here, if you wanted to get the cosecant function, it's under here, functions, trig, cosecant. So you can just type cosecant x, unlike your calculator. Most calculators don't have a cosecant button. Well, let's look at the images right here. Let's see if I can run this at pi over 4. Okay, Desmos complies. So where is it equal to 0? Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So I really want to reinforce this with you. You can always see whether you have the right numbers. If you were approximating, yes, I'd only see approximate numbers here. Okay, but I can always graph something and see if I'm in the right ball game or if I'm way, way off. It's kind of a pretty picture. Now, by the way, if I expanded, since this is a periodic function, this is going to be 0 many times. But between 0 and 2 pi, it's only 0 those 4 times. So what if the book had said to you, we want all solutions? You could say each one of these plus 2k pi. Let me go back to my paper. But that would be a lot of writing. Why don't you just take pi over 4 plus 1 pi plus 1 pi plus 1 pi? In other words, you could say, you could cover all 4 of these and all their multiples by saying pi over 4 plus k pi, because pi is halfway around, or 3 pi over 4 plus k pi. So that'd be one way to present all solutions without a lot of writing. If you said plus 2k pi for all 4 of these, go ahead. It's not wrong, just extra writing. Remember, this k can be positive or negative, so this covers going forwards or backwards. And in our image, we can see that. So if I expanded this image, I would see that those 4 answers repeat over and over and over again. Okay, so there would be the next answer right there, 9 pi over 4, 11 pi over 4, 13 pi over 4, 15 pi over 4. Okay, so the graph is handy. Okay, I'm going to pop out of there. Let me see if I can pick one more. So doing these problems and they're sneaking in the other trig functions. So that means you've got to prep the problem. It means you've got to do some simplifying before you start. Now you got some secants and tangents in there, but here's a half angle one. Let's try that for our last problem today. Because that requires what? That we remember the half angle formula. grab our formula sheet in case we need it. Let's look at 31. So good news, bad news. This is up to you. Now, they want this in radians, so I'm going to write it down exactly what I did last time. They want apparently exact answers still in this section. I'm still in the same section, degree answers, blah, 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 blah. Okay, they want exact answers. They want in radians. And they want 0 to 2 pi. It's not bad to write this at the beginning of every problem. Cosine x over 2 minus cosine x equals 1. So here I got to play another game to bring these together. I can't have half angles and full angles. I have to replace the cosine of x over 2. So I use the identity. Unfortunately, the cosine of x over 2 could be positive or negative, right? So let me rewrite this first. Cosine of x over 2. I'm not saying this is going to be super exciting. Cosine of x over 2 is 1 plus cos x. That's what I'm trying to solve. But now I'm going to replace this with the formula for cosine of x over 2. It was a little too crowded right there. So the cosine of x over 2, you know your half angle identity, plus or minus 1 plus cos x over 2. Now, the only is that you think you made something worse. In the sense, you did make something worse. You invited the square root into the problem. So in order to get that square root out of there, I think I'm going to square both sides. That means I have to square both sides honestly. That means you FOIL out this side. 1 plus 2 cosine x plus cosine squared x. So you have to remember how to FOIL. Over here, squaring the plus minus is kind of irrelevant. It's going to be plus either way. Squaring the square root is also going to make it look simpler. So this is messy, but at least everybody's in terms of x. That's what I wanted. 1/2 plus 1/2 cos x equals 1 plus 2 cos x. Plus cos squared x. So now I'm going to bring the half over here. I'm going to bring the half cos x over here. That's 2 subtractions. I'm going to write this in order. Cosine squared x plus 3/2 cos x. Excuse me. Plus 1/2. Before I do the quadratic formula with fractions in it, which I really don't think I'm going to enjoy, it's still legal for me to multiply both sides by 2. So if you have a choice, why use fractions in the quadratic formula? So now let's write the quadratic formula. Opposite of b plus or minus square root of b squared minus 4 times a times c divided by 2 times a. Make sure you put the numbers in the right place. The opposite of b is the opposite of 3. B squared is 3 squared. A is 2 and c is 1. It's not a bad deal here. We're going to get some nice simplifying, I think. Bottom, 2 times a is 2 times 2. Let's see what we got. -3 plus or minus. Notice this is 9 subtract 8. If you want to write that out, you go right ahead. But 9 subtract 8, this is just a giant 1 over 4. The square root of 1 is 1. So this is -3 plus 1 over 4, or -3 minus 1 over 4. So now I found out what cosine x is, and now I can go for x. This would be -1/2, and this would be -1. Draw 2 different pictures, just so things don't get too cluttered. If the cosine of x is -1, you are over here. -1, 0 with a radius of 1. Remember, on the unit circle, this point is cosec sine x. And we're talking radians. Let's try to remember he wants radians this time. So there's the only answer with cosine -1, x equal pi. Cosine of -1/2 means I have x over r of 1 to 2, but the x is negative. This is a famous triangle. So this side is √3 plus, and this side is √3 minus. Practice totally labeling your picture like this, as he does in the book. This is 2/3 pi. This is 1/3 pi past the full pi. That's 1 1/3 pi. That's 4/3 pi. And so here's the final answer, and I will rush over and graph this so I keep making that point in your mind. So these are very meticulous problems, right? You got to do every step correctly, but you can see the right answers when you're done. That's a positive thing. So what if I had typed in here cosine x over 2? Now these parentheses are important, right? Sorry. Subtract cosine x. And remember, the problem said this was equal to 1. So I'm going to write y equals 1 here too. And I'm going to expand. No, not expand like that. So let's graph this from 0 to 2 pi. Got it. Pi over 4s. I'm getting pi and 1. That's good. I'm getting 2 pi over 3 and 1. That's good. Where am I getting the 4 pi over 3? This is interesting. Did I miss something? So let's examine this 4 pi over 3. And this is why we have to test this, right? Let's think about this. What happens when I squared both sides? I created something that was true from something that was false. You always have to think about this. Squaring both sides is legal, but it can take something that's false and make it true. -1 and 1 are not the same, but after you square them, they look the same. And that's what I did here. This answer of 4/3 pi looks good in this problem, but it doesn't look good in that problem. So we got to add this to our list of things to do now. Check the solutions. And the cosine of 2/3 pi minus the cosine of 4/3 pi is not 1. I have to cross out that answer. I'm going to bring some other examples like that next time because we got to call it a day. But yes, whenever you do something like square both sides, remember that's legal, but it might create some false paths for you. Here's another reason why you want to graph to see the answer. Okay, when that happens, people call that an extraneous solution. Okay, I'm gonna have to cut it off there. So I'll let you guys start working on this. We'll do more like this next time. Just we'll bring in fancier functions and things like that. And we'll do some more checking to see extraneous solutions like this. Okay, you guys have a good day, and I'll see you again on Wednesday.